Hello and welcome to this last video in our lecture on digital envelopes and pseudo-random number generators. In the previous video, we discussed the difference between true and pseudo-random number generators. In this video, we're going to describe a specific pseudo-random number generator named BBS, named after its creators, the famous mathematician slash computer scientist couple Leonard Bloom and Manuel Blum, and the mathematician Michael Shub. This algorithm was proposed in 1986, and it is an example of the kind of pseudo-random number generator that we described, whose structure we described in a previous video. So remember, the general structure was to use a deterministic algorithm as the core of the process, and this algorithm was fed as input a single seed number, and it will output a sequence of pseudo-random bits, and the way this sequence of bits is produced is in stages, whereby this initial value is used to compute the value of some quantity in this algorithm. That quantity will be called x, and then the value of x at the end of a given stage is going to be fed back as input to be used as the value of x for the next stage. So this is an iterative algorithm, and because it outputs a sequence of bits, we're going to call it a pseudo-random bit generator. So the algorithm, the BBS algorithm, is described right here. The first step is to pick two big prime numbers, P and Q. So in our sample trace, we're going to obviously use very small values so we can do the computations easily. So P, we're going to pick to be 11. Now notice one constraint on these prime numbers is that they're both equal to 3 modulo 4. So because 11 is equal to 8 plus 3, and 8 is a multiple of 4, it satisfies this congruence. And similarly for Q, must have the same property. We're going to pick Q equal to 19, which is equal to 16 plus 3, and 16 is a multiple of 4. And then we're going to conclude step number 1 by computing the product of these two prime numbers, which we're going to call n. And in this case, 11 times 19 is going to be equal to 209. So all the computations afterwards in the algorithm will be done modulo n. That's why this number is important. And this number must be equal to the product of two prime numbers, each of which is 3 more than a multiple of 4. Okay, the second step in the algorithm is to pick another number called s, which is essentially the seed in this process. And the only constraint on s is that it be relatively prime to n. So it should not have any common factors with n other than 1. So we're going to pick a small value here, namely 3 for this trace. And then we're going to start the main loop of this algorithm. And before we get into the loop, we have one last initialization step, is we're going to compute the initial value x of 0 of, this is the quantity that's going to be fed as input and produced as output by the algorithm at every stage. So we're going to initialize x0 to the square of s modulo n. So it's going to be 9 squared modulo 209, which is 3 squared, which will be equal to 9. So x0 is really the initial value that is fed to the first stage of the algorithm. And the stages are going to go from 1 up. So according to the loop variable I, and notice we have an infinite loop here. Really what this means is we're going to execute this loop as long as we need more bits. So we're not going to run it forever, we're just going to run it as long as we need random bits. And the body of the loop is relatively short. It works like this. At every iteration of the loop, we're going to take the current value of x, meaning the value of x that was produced by the previous stage, and we're going to square that modulo n and assign the resulting value to x to become the new value of x. Then once we have the new value of x at the end of this stage, we're going to use it to extract the output bit b sub I. And the output bit is simply going to be the result of taking the current value of x modulo 2. In other words, the output bit is nothing but the least significant bit of x. So if x sub I is even, the output bit will be 0. If x sub I is odd, the output bit will be 1. This is, in a nutshell, the BBS algorithm. So let's trace it on the first 3 iterations, say. So in the first iteration, we're going to compute x sub 1. That is going to be x sub 0 squared, so 9 squared modulo n. Of course, 9 squared is 81, modulo 209 is still 81. So the first value of x, or at least the first output value of x, because notice we do not generate a bit corresponding to x0. You should consider this an initialization step, okay? The first bit that's output is the least significant bit of 81, which is 1, because 81 is an odd number. So this is the first bit in our pseudo-random bit stream output by the algorithm. So let's do the second iteration for I equals 2. We're going to square the previous value of x, take that modulo n. Now it turns out 81 squared is 6561. So take that modulo n. So when we do the integer division of 6561 by 209, we end up with a quotient of 31 and a remainder of 82. So this is what 6561 is equal to. So when we take this modulo 209, obviously we're left with the remainder, which is 82. And 82 being an even number, that means the next bit output by our algorithm is 0. Okay, that's the end of the second iteration. So for the third iteration, we're going to take the previous value of x, which is 82. We're going to square it, modulo n. Now 82 squared is 6724. So modulo 209. That is actually, so now we're going to do the integer division of 6724 by 209. And the quotient is going to be 32. The remainder is going to be 36. So of course, when we take that modulo 209, we are left with 36. This being an even number, the third bit output by this algorithm is going to be 0. So this is a partial trace of the BBS algorithm when picking 11 and 19 as the two prime numbers and s as of equal to 3 for the seed. So this is a relatively simple algorithm. Now remember that in practice, the p and q and s are going to be very big numbers, but still, as long as you can do modulo and operations and multiplications, that is extremely simple to compute. Now the reason BBS is a very popular algorithm is because it has a very strong proof of security. So what does it mean for a pseudo-random bit generator to be strong? Well, what it means is suppose you're given the beginning of a sequence. So we know this sequence in this case is going to start with 1, 0, 0. And let's say I'm going to make up the following bits here in this sequence. So let's say that you've produced k bits, and the question is to predict what the next bit is going to be. Now notice if you don't have any information and if you don't know any relationship between those bits, or if this sequence is completely random, then the best you can do is just take a guess, and then you have a 50-50 chance or probability of 1/2 to guess the right value. So if this algorithm is secure, that means you should not be able to do better than just chance. And so there is a test for this. This is called the next bit test. So the next bit test asks the question, is there an algorithm that given the first k bits of a sequence can compute the next bit, the k plus 1 bit? And what I mean by that is it's not just that you have to know the bit for sure, but you can predict it with a probability that's significantly greater than 0.5. So we're not even asking that you know it for sure, but can you predict it with, say, a probability of 0.75, 3 times out of 4? If such a test exists, then we say that the algorithm is not very secure. So really the output that we want for this test is that the output should be a no. There is no algorithm to do this. And by the way, when we say algorithm, we mean a tractable algorithm, which in complexity theory means a polynomial time algorithm in the value of k. So it could be a quadratic algorithm or a cubic algorithm. Any polynomial would be acceptable. But to pass the test, the so-called next bit test, it must be the case that there is no such polynomial time algorithm that will guess the value of the next bit given the values of the first k bits, with a probability that's significantly different or greater than 0.5. And it turns out that the authors of this algorithm, Blum-Blum-Shub, were able to prove that this algorithm does have this property. It does pass the next bit test. And this is a very, very strong property to have. And by the way, the strength of this algorithm relies on the fact that the factorization of large integers is a difficult problem. Notice this is the same property we assumed when we evaluated the strength of the RSA algorithm, which was in a way similar since it started with picking 2 prime numbers and then multiplying them and then computing phi of n, if you remember. So the bottom line is that this algorithm is not only really simple, but it was designed very carefully in such a way that it passes the next bit test and therefore is a cryptographically secure pseudo-random number or pseudo-random bit generator. And I'm going to conclude this lecture by reminding you that this algorithm does exhibit the general structure for pseudo-random number generators that we discussed in a previous video.